Alright, let's see if we can maybe talk about variables and bring this back to Cheat Engine in some sort of way. Been typing a lot in Notepad. May or may not make sense. I'm hoping it does, but let's see if we can tie this to Cheat Engine in a way that is readily useful for us. So let's think of a contrived example here. Alright, we're going to do that. Doesn't matter, we're just going to pick a random process. See if we can make it more amusing. See if we can have Cheat Engine attached to itself. Yeah, we can do that. It's great. I don't know. Type in something. Is it really scanning itself? It is. It's scanning itself. That's pretty awesome. Anyway, from here on, we're going to assume that variable names, like all the rules that we went over in the previous video, variable names cannot start with numbers, cannot contain punctuation. The outstanding and encouraged exception. Underscore. You could use as many underscores as you want. So some really freaking long value equals, I don't know, some constant. That's totally valid. Yeah, you could string underscores together with characters and whatnot as much as you want. So, quick recap. Valid characters for variable names include, put a little space here, get rid of some of this crap on the bottom. Again, don't worry, I know we're still typing in Notepad, but I have a plan. Valid characters for variable names include A through Z, lowercase, A through Z, capital, and the underscore. That's it. Purposes of this video series, we're never going to step outside the bounds of these three simple rules. It's a lowercase letter, it's an uppercase letter, or it's an underscore. Never a digit. Doesn't matter where in that identifier it happens. It's some value with a long name. Is that valid? Is that a valid variable name? Sure. Is that valid? No. Why? Because there's a number. Yeah, there's a number. That's all we're gonna say. So that's the hard and fast rule we're gonna adopt for the series. If you're interested in the technical reason as to why this exists, kind of abstracting a little bit of it. Is this a hard and fast rule with real programming languages? Yes and no. There's some subtlety which I don't really care to get into right now. So, the outstanding and encourage exception to the alphanumeric rule, the underscore. See if we can demonstrate this. Cheat Engine, open, scanning itself. We have to put in a value. Let's put in 1, 2, 3. See what we get. Put in 1, 2, 3, 4. See what we get. We get nothing. Really? Yeah. How about 1, 2, 3, 4, 5? Shit. Alright, we'll go with 1, 2, 3. We're gonna just pick a value at random. Whatever. Say this is the value we want. Pretend there's nothing else. Oh, we got the value. That's great. So, what do we got here in Cheat Engine? It gives us the active box, allows us to freeze and unfreeze the value, gives us a description, gives us an address for that value relative to the start of the process. How is Cheat Engine interpreting this value? It's 4 bytes. We can make it 2 bytes. It's 1, 2, 3, so it's below the cap. We can make it a byte. We can make it binary, but it's just going to be a 1 or a 0. But, the hell with it. We'll do it anyway. Yep, 4 bytes, whatever. We'll go back to that. So, the value as interpreted by Cheat Engine when it applies this data type to this bit pattern is 1, 2, 3. So, it's no different when you're dealing with scripts and whatnot in programming languages. Say we have x equals 1, 2, 3. So what we're going to do is we're going to kind of take these columns in this item right here, this record, if you will, that Cheat Engine gave us. We're gonna try and sort of express some of that down here in Notepad, break it down a little bit, go over it in a little more detail. There's actually there, as a matter of fact, there is more detail. You may be asking yourself, how the hell is there more detail? There is. There's always more detail. It's just the way it is. So for our case, let's say we want to kind of rewrite this in a programming language, our pseudo language that we're making up, if you will. So what are we gonna do? Well, we can say we have a variable, we have a type, we have a value, there's a description, and then whether it's frozen or not. How are we possibly going to express all this information? Well, as we talked about, you can, in a programming language, you can say x equals 5. What does that mean? Takes the value 5, it assigns it to the symbol x, and then whenever the computer sees the value x, it'll just replace it with 5. It's very simple stuff, very basic, absolutely, probably one of the most basic concepts of computer science. So, how are we going to express this? Well, we're going to start breaking this down. What's the value that we want to assign to a symbol? 1, 2, 3. What type is it? It's 4 bytes. We're not really going to deal with that. But now we get into the, as you can see, we're kind of working backwards here. What's the value? Then we go to the type. Then we go to the address. Then the description. And then we go to the active flag, if you will. It's active or not. There's only 2 basic things that we're going to deal with here. How to express the value, which we've already done. So 1, 2, 3. It's real easy. What's the type? We're not really going to mess around with that right now. And then from this record, we're going to want to deduce, what is this? How do we express this? Well, we could come in and just put in the equal sign. So what are we missing? Well, we're missing the side on the identifier or the symbol or the variable name. They're all synonymous on the left. How are we going to do that? We could take the brute force approach and just do that. Is this valid? In programming language, it is not. Why? Because it violates our fundamental rule of you cannot start a variable name with a number. So we have to get rid of that. And plus, that would be meaningless. This value on the left is just a name. It's just symbolic. It has no meaning relative to absolute memory addresses or anything like that. So how are we going to express this location in memory to our variable? We don't really have to worry about it, because in the translation that we're doing here, this value is this is a memory location relative to the process that has a value. This value is going to change, or this address is going to change when we reallocate, deallocate, or relaunch the program. So what we want to do is we want to abstract away in some deterministic way the address for this location, or for this value rather, in memory. How are we going to do that? Well, in the context of our programming language, we're just going to say just some name. That's it. Do we care that it doesn't have this actual address? No, because again, we're translating a lower level thing into a somewhat higher level concept. So drilling down here a little bit, we know that 1, 2, 3 is now assigned to the variable name some name. We make some other variable, do some other name. What's the value of some other name as a variable? It's going to be some name plus 1. Just going to keep it real simple. Basically, we're laying out the same example that we talked about in one of the previous videos. Computer's going to read this statement. It's going to take this value. It's going to assign it to that name. It's going to come down here. It's going to find this name. It's going to say, all right, I have this new variable called some other name. What are we going to assign? What's the value that we're going to assign to it? Well, we're going to get some name, and then we're going to add 1 to whatever some name is. How is it going to find some name? It could jump into a symbol table, or a sort of a lookup table, and I'm sure it will. Most programming languages and whatnot, they will do something like that. It's just typically 10 minutes. They have some sort of abstraction there where every variable is defined in some kind of lookup table or dictionary data structure, something like that. But under the hood, what it's doing is, it says some other name. What does it equal? It equals some name plus 1. What is some name? Refers to a previous variable, goes into the lookup list or the dictionary, finds some name, and then it says what's the value of some name? The value of some name is 1, 2, 3. We've gone over that, but what is actually going on a very, very low level is that what we're going to do is we're going to rewrite these two statements. Do some name equals 1, 2, 3. So what the computer's going to do is it's going to assign 1, 2, 3 to a variable of some name, but it's gonna put some name in a lookup table or in a dictionary, as it were. That's fine, but then again, we'll drill down here a little bit. What it's really gonna do is it's gonna make new memory for this variable, and it's going to say, it'll just allocate that memory on the fly. It'll get an address similar to this address right here. We'll just add something to that address, but we're going to copy it for the time being. So what is the computer really doing when it evaluates this right here? What it's really doing, just change this to let me see, we'll add 4 DEF 0. It's saying, we're completely choosing this address, just pulling it completely out of our ass. So that address is going to be 1, 2, 3. Now, when we want to make some other name on a human level, again, this first statement is what we write and what we read in a programming language. What does this evaluate to under the hood as far as a computer and how it understands things? This is what the first statement becomes. It's going to take some name. It knows that we're assigning a value to a new variable or an existing variable. We'll get into that. So does some name exist? It does not. It's going to make a new variable. What is the memory location of that new variable? It's this address right here relative to the process. It's going to take that memory location. It's going to stuff this value 1, 2, 3 into this memory location, and then any other time that we see that it sees rather this symbol, the variable name, it's going to substitute the value located in this memory address. So some other name equals some name plus 1. What is the computer going to read that as? It's going to read that as some other name equals some name 035 B60 D0 plus 1. That's what the computer is really going to do. And then, as a matter of fact, if you want to get more pedantic, sort of again bringing this example down in a somewhat recursive way, getting down there. I have to hurry up here a little bit. What it's really doing is saying some other name does not exist as a variable. Going to make a new one. We'll just call it 035 B60. I don't know what something that comes after it, F0 equals the value at the memory location 035 B60 D0 plus 1. So if we were forced to write this illustrates why variables exist at all in computer science. It's, it's talked about descended from mathematics, and so they have to exist for certain abstract reasons, but on a functional, pragmatic level, variable names exist so that we don't have to type actual memory addresses around. The computer compiler, interpreter, whatever you want to say, will basically take care of this whole process right here behind the scenes so that we never have to worry about, maybe not never, but certainly almost never have to worry about what the actual memory location address for a value is. We just make a variable name, we give it a value, and behind the scenes the computer keeps track of whatever the hell location was assigned to this name, and then whenever it sees that name, it looks up that location in memory. In this case, it might be 035B60DC, pulls out the value in that address, substitutes it in, completes the calculation, assigns that value to a new variable, and if it has to, it'll dig up a new memory, it'll allocate new memory for that variable. And that is essentially variable substitution in a nutshell for us.